Our next speaker is Galo, who's going to speak about transferring PCM-F1 digital recordings to current digital standards. Galo retired in 2014 after 38 years as audio engineer at the Crane School of Music at SUNY Potsdam, where he also taught courses in music literature and audio technology. He has been an ARSC member since 1982 with multiple roles. He was the sound recording review editor of the ARSC Journal from 1995 to 2012, was co-chair of the ARSC Technical Committee from 1996 to 2004, has been a frequent presenter at ARSC national conferences and New York chapter meetings, and has written numerous articles, book reviews, and sound recording reviews for the ARSC Journal. Mr. Galo is a widely published author with over 300 articles and reviews to his credit on both musical and technical subjects in over a dozen publications. He is a regular contributor to Audio Express magazine, has reviewed numerous books for Notes, quarterly journals of the Music Library Association, and is the author of the loudspeaker entry in the Encyclopedia of Recorded Sound in the United States. Mr. Galo is a member of the Audio Engineering Society and the Société Wilhelm Furtwängler. Please welcome Galo.
Thank you. Nice to be here. How many of you were at the New York chapter meeting in April? Just a couple. Well, what you heard then was a more extended version of the paper I'm giving today. This is more a Reader's Digest overview of this subject. Does everybody have a handout? There are extra copies of the handout on the front table here if you don't already have one. How many of you have never worked with a PCM-F1 recording system? Quite a few. Okay, good. The PCM-F1 was a digital recording system processor introduced by Sony in 1981, and like a lot of early digital recorders, it encoded the digital data stream on a video carrier and it stored the data on videotape. Now you could use either Sony's beta format or JVC's competing VHS system. I've even heard of one or two people tell me that people sometimes used U-matic for PCM-F1 storage. No reason why it couldn't be done. Now, because the formats for digital audio were not yet standardized, transferring these old digital tapes to current digital standards is not completely straightforward, and that's what we're going to explore today. Now, one of the reasons the PCM-F1 attracted a lot of attention was portability. The physical size of digital recording systems had been reduced considerably since the first digital audio recorders appeared in the early 1970s. These Denon digital recording systems from the 1970s were literally a truckload of equipment, and storage was on 2-inch reel-to-reel videotape, not exactly portable. In 1978, Thomas Stockham's Soundstream digital recorder was quite a bit smaller, but as you can see from the size of the road cases underneath his table here, it still was a ways from being portable. So the PCM-F1 was a breakthrough in both portability and price. The processor sold for under $2,000, and it was designed to be stacked with Sony's SL2000 portable beta recorder. Nakamichi also sold their own version of the PCM-F1 processor under license from Sony. It was physically identical to the Sony PCM-F1 except for the color scheme. The Nakamichi version had improved analog circuitry and guaranteed performance in the A to D and D to A converters, and the Nakamichi version is the one that I used back in the 1980s. Now, there are 4 issues that you need to deal with in transferring PCM-F1 tapes to modern digital standards, and I'm going to talk about each one in more detail shortly, but here's an overview. First of all, the sample rate was 44.056 kilohertz. Now, for a long time, sample rates have been at multiples of either 44.1 or 48 kilohertz. But I have to note that 44.056 only applies to recordings that were made on NTSC-based systems. The sampling rate for PAL systems was 44.1. So if you made tapes with a Sony F1 processor that was made for the PAL system on a PAL recorder, you don't need to worry about the sample rate. But for NTSC-based systems, you most certainly do. The second thing is that all PCM-F1 recordings were made with preemphasis, which is a high-frequency boost applied during the record process. Now, the PCM-F1 followed the 50 microsecond, 15 microsecond curve that would become part of the Red Book specifications for the compact disc, and again, we'll talk more about that in detail shortly. The third thing is that the two channels are not in phase. There's an interchannel time delay that has to be corrected. And finally, PCM-F1 tapes also have DC offset, and that is something that needs to be corrected. Now, there's one big problem with the PCM-F1. This processor did not have a digital output. So the only way to transfer these tapes to a new format was to use the analog outputs and feed them to the analog inputs of another digital recording system. But this is not a good solution because it adds two unnecessary conversion processes plus a whole lot of analog circuitry. And even if you have excellent converters in your digital recorder, you're still saddled with the limitations of the F1's D to A converters and analog circuitry. What you need is a later Sony processor with an SPDIF digital output. The one shown here is the PCM-601 ESD. This was the first F1 compatible processor that had an SPDIF output. I actually believe it was the only one they made that had an SPDIF digital output. It looks very similar to the earlier PCM-501 except for the addition of an SPDIF input and an SPDIF output on the rear panel. And the SPDIF output is this big bulging unit that sticks out the back that looks like something they tacked on to the old PCM-501. These turn up on eBay. They don't turn up very often, especially at reasonable prices. You just have to keep looking. Now, everybody has their own approach to doing digital transfers. This is the recorder I use for my own transfer work. It's a Tascam DA3000, and it has to be one of the best buys in digital audio today. The list price is $1,000, but quite a few dealers are now selling it for less than $800. I have two of them in my studio at school and one at home. Now, the DA3000 has no moving parts. It records PCM at up to 192 kilohertz 24-bit. It also does direct stream digital, which is not going to be of any use in this application. And it stores everything on SD memory cards, so once you do an initial transfer, you take the SD card, plug it into your computer, copy the files to your hard drive, and go to work. It also has a built-in switchable sample rate converter, which is based on the Cirrus Logic CS8422 sample rate converter chip. Now, the sample rate converter chip also does Red Book Deemphasis, but very strangely, this feature is entirely undocumented by Tascam. There's absolutely no mention of it in the owner's manual, and I'll talk more about that shortly. These are the settings that you need on the DA3000 setup menu in order to do the sample rate conversion. First, you have to turn the sample rate converter on, and under File, you select Wave24 for 24-bit PCM wave files, and you set the sample rate to 88.2 kilohertz. Now, the original PCM-F1 could record with either 14 or 16 bits of resolution, and that was selectable with a rear panel switch. I recommend converting the data streams to 24-bit. This will make any signal processing you do on your editor more accurate, even if it's just normalizing levels down the road. And a bit later on, I'm going to explain why I convert the sample rate to 88.2 rather than 44.1. Let's talk about the Red Book Preemphasis and Deemphasis standard. This was an option for early CDs, by the way. It wasn't mandatory. Now, the so-called Red Book was the Sony Philips document that contained all of the standards for the compact disc, and the standard that they specified for preemphasis had already been in use when the CD was introduced in 1982. Now, preemphasis is a high-frequency boost that's applied during the record process, and the preemphasis curve, which I've shown in red in this graph, is defined by two time constants, 50 microseconds and 15 microseconds. Now, 50 microseconds corresponds to 3.183 kilohertz, which is where the high-frequency boost begins, and in a record, the filter response is 3 dB up at that frequency. The 15 microsecond part of it refers to the frequency where the high-frequency boost is shelved, and this takes place at 10.61 kilohertz. The Playback Deemphasis, which is shown in blue on this graph, is the exact complement of the preemphasis curve. Now, when preemphasis was first conceived for digital recording, most converters were 14-bit, and the preemphasis was applied with an analog filter before the A to D conversion took place. And its purpose was to overcome low-level, high-frequency linearity problems inherent in the A to D and D to A converters of that time, and extend the resolution of the converters beyond 14 bits at high frequencies. In the early digital recording, playback deemphasis was also done with an analog filter after the D to A conversion. Now, since the introduction of 24-bit converters, playback deemphasis on older recordings has normally been applied in the digital domain, often in the digital filter ahead of the D to A conversion process, but it can be applied elsewhere, and we'll see that shortly. Now, although a lot of early digital recorders used preemphasis, not very many CD manufacturers adopted it. Nearly all of the CDs that I have in my own collection were made in Japan by Denon. And by 1990 or so, the converters had improved to the point where preemphasis was no longer necessary, and the handful of CD manufacturers that used it stopped doing so. Now, this is an inside view of the DA3000 recorder from the Tascam website, and as you can see that they're very proud of the various components on the main PC board, including the Burr-Brown A to D and D to A converter chips. There's a typo there, the op-amps is instead of op-amps. One thing they don't point out, very strangely, is the Cirrus Logic CS84 sample rate converter chip, which is on the digital input-output board. They also have a block diagram on their website. Now, I've circled the CS8422 sample rate converter chip in red in the block diagram. The CS8422 also incorporates the digital input receiver and the input switching, and that's shown in the diagram, but there's no indication that this chip also performs deemphasis. So, I went to the Cirrus Logic website, downloaded the datasheet for this chip, and the datasheet clearly shows that the chip performs deemphasis. So, the DA3000 digital recorder takes care of two problems right off the bat. It takes care of the sample rate conversion, and it takes care of the deemphasis, which leaves two more to deal with. Now, I know some of you may prefer to record directly to your computer workstations, so you'll need to put a sample rate converter between your PCM-601 and your computer's digital input. Now, I know there are some people out there who will tell you that you can feed the 44.056 kilohertz data stream directly to your computer and do the sample rate converter with the software in your editor. I strongly advise against this because most computer SPDIF input receivers, in fact, most input receivers, period, will not achieve a proper digital lock. And without a proper digital lock, jitter is likely to increase. And as we saw in the previous presentation, yes, jitter is something that we need to be concerned with. There aren't very many outboard sample rate converters available anymore. This is a high-end model from Mytek, the Stereo 192 SRC. You need, whatever sample rate converter you use, it has to be asynchronous. The Mytek certainly qualifies. This is the same as for a variable pitch application. And the two sample rates are about 0.1% apart. So it's really no different than changing the speed on your variable pitch CD player. You change the sample rate by 0.1%, you need to go through a sample rate converter so your D to A converter will actually recognize the data stream and lock onto it properly. Now, if you're on a budget, which many people are, this $200 Behringer SRC 2496 actually works very well. It uses an earlier generation Cirrus Logic sample rate converter chip. It will convert 44.056 to 88.2. One thing it won't do is it won't perform deemphasis, at least not if you use it as a sample rate converter. It will if you use it as a D to A converter, but not as a sample rate converter. So we have to deal with that another way. There are other solutions to the deemphasis issue. Now, this preset is included in Isotope's Mastering Equalization. It's part of the Isotope Mastering Bundle that comes with SoundForge 11 and 12 Pro. I've measured the accuracy on it. It's plus or minus 0.4 dB, which is adequate. It's probably no worse than the analog filters that created the preemphasis curve in the first place. If you want to experiment with your own computer equalization plugins and create your own deemphasis curve, I have frequency and level data for the Redbook deemphasis curve based on a computer simulation that I did a number of years ago. And if you want to do an experiment creating your own, just email me and I can send you the raw data and you can fiddle with it and see how close you can get it. Now the PCM-F1 A to D and D to A converter chips actually had one converter that switched back and forth between the left and right channels, and what this caused was a time delay between the two channels that's equal to half a sample at the sampling frequency. Now, the analog to digital and digital to analog converter delays were complementary, so there was no time delay at the analog outputs of the F1 processor. But the analog to digital converter delay got recorded, and it needs to be corrected if you're doing a digital transfer. I'm not going to spend much time on this. The formula's on the handout. These are the formulas, or the formula for calculating interchannel time delay if you know what the sampling rate is. The bottom line here is that the difference in time delay between half a sample at 44.056 and half a sample at 44.1 is 0.011 microseconds. Short in a little bit, we'll find out if that difference is anything to get excited about. Now, when I was developing my own procedure for transferring PCM-F1 tapes, I recorded 1 kilohertz and 10 kilohertz test tones on my original F1 processor, and then I transferred them to the Tascam DA3000 using the PCM-601 processor. But rather than convert the data stream to 44.1, I set the DA3000 sample rate converter to 88.2 kilohertz. Now, if you record a 10 kilohertz test tone with your original F1 processor and transfer it, you can see the delay between the two channels. The time delay is now one sample at 88.2 kilohertz rather than half a sample at the original frequency. And in this illustration, cursor 1 is on the right channel and cursor 2 is on the left channel. And you can see that the left channel lags behind the right channel by one sample. You have to remember that time moves from left to right in the editing window. Now, the phase difference at 10 kilohertz is 41 degrees, which is pretty serious. I've had a couple of people suggest to me that interchannel time delay is not audible. I would suggest to you that if you had an analog tape that was 41 degrees off at 10 kilohertz, you would not let that go. It is definitely something that needs to be fixed. So all we need to do is delete one sample in the left channel to bring the two channels into alignment, and most digital editors will allow you to do this. The sample rate of your transfer has to be at 88.2 kilohertz. That's why I do it this way. I don't know of any editors that will allow you to delete half a sample. One sample is normally the smallest division that you can highlight and remove. So I highlight one sample in the left channel, I hit the delete key once and only once, and now, as you can see in the right illustration, the left and right channels are in alignment. Easily done. Now, if you want to get really picky, you can use a phase corrector to align the channels. Now, this is a phase corrector that comes with Adobe Audition 3.0. The sample rate in this case can be either 44.1 or 88.2 kilohertz. You have to use the global time shift, and what you do is you set the left channel to minus 11.35 microseconds in the window here where you enter that data. Adobe Audition's sample rate converter, 3 minutes? Okay. Adobe Audition sample rate converter only allows 2 decimal places. Now, you probably think that the correct time conversion for half a sample at 44.056 is more accurate than upsampling to 88.2 and deleting one sample. In reality, that's true, but in fact, the phase difference between the two methods is only 0.04 degrees, and if you can hear that, you've got better ears than me. Let's talk briefly about DC offset. DC offset amplification circuits typically have some level of DC at the input and or the output, which is basically the zero crossing for the audio signal. And if that zero crossing becomes too high or too low, then what happens basically is that it limits our headroom. So in this illustration, we can see a sine wave basically at maximum recording level. In the middle, we have a sine wave where we have clipping, and with no offset, the clipping is symmetrical. Over on the right here, we have a DC offset level, which is way too high, and it causes asymmetrical clipping. The top half of the waveform is clipped, and all this space down here is wasted, and that's what basically eliminates headroom, or reduces headroom. So that's not a good thing. We have to get rid of it. DC offsets were a problem with early converters, and the service manual for the PCM-F1 had a trim adjustment for getting rid of it. The tip-off that you have DC offset is that you'll see very high levels in silent passages, and if you zoom in vertically, you can see that the zero crossings are not exactly at zero. Most editors have a plug-in that will allow you to eliminate DC offset. It'll bring the levels down, and it will also, if you zoom in vertically at the same rate, you'll see that the zero crossing is now at exactly 0 dB. There are free plugins. Adobe Audition and Audacity are free programs now, and they have DC offset removal tools as well. So that's an easy way to do it. All right, very quickly, 2 more slides. If you're just getting started doing transfers of PCM-F1 tapes, I've got a couple of suggestions that will help you verify that your procedures are working. First of all, I suggest recording 1 kilohertz and 10 kilohertz test tones, sine waves, on your old F1 processor. A few minutes at each frequency will be fine. And if you set the level on the 1 kilohertz tone to -10 on the F1 processor, don't change the level for the 10 kilohertz tone. The meter will now read -2.4 at 10K because the metering reflects the preemphasis. So after you've recorded the tones, you can change your processor to the PCM-601, transfer the test tones through a sample rate converter to your digital recorder or directly to your computer. And then you can use the test tones to verify deemphasis and interchannel time alignment, the same way I did for the illustrations in this slideshow. Finally, I think you'll find that your old PCM-F1 recordings sound a lot better than you originally thought. And by bypassing the old A to D converters and the old D to A converters and analog circuitry in your F1 processor, and by doing the conversion and analog playback with the equipment that we have today, you eliminate a serious limitation in the PCM-F1 system. We heard some comments earlier this afternoon about keeping old equipment working. The biggest problem here is keeping your old beta machine working, which may not be an easy task. If you have problems with dropouts, check the tracking adjustment. There were a couple of auto tracking machines that Sony made near the end of the PCM, or near the end of the beta format's existence, I should say. They're very desirable machines if you can find them. I wish I had one, but I don't. So there is a brief summary of how to transfer PCM-F1 tapes. Thank you very much.
Thank you, Gary. Any questions for any of the presenters?
Yeah, I have a question on ADC test. We saw the analysis of pre-recorded or pre-formatted data, but I must have blinked because I didn't see how that data was acquired. Could you cover that, please?
Sure. So in the scenario that I showed, those files came from the vendor. So in that case, the vendor would have been supplied with the guidelines, and they could create the files that way using their system, how the items will be transferred using the ADC that they will be using. It's a signal generator.
Just one frequency? Or?
Oh no, it's a long guideline specification.
It's like an encoded decode system. She only showed the back end of it, so she didn't show how the test.
Yes, well that's my issue, because I couldn't get anything from that without the whole issue. So just some notes that you could tell me how to do?
Oh, sure. On the last slide, there were all the guidelines, the links to them. So you can go ahead and check those out for sure. Do you want to?
So I'll just say that the FADGI guidelines, there are links in the last page of our slide, and we can circulate those slides. The FADGI guidelines go into great detail about how to capture that data and then to analyze that data using the ADC test software.
Photograph that slide, so we're going to do that.
Okay, thank you.
Thank you.
I just want to mention that thank you, this was very informative for the PCM-F1 tapes, and having been around Sony through many iterations of their digital technology at the studios, a lot of this can also be transferred, a lot of this information is relevant to the early 1610 units as well, where we were also still dealing with 14-bit converters and the Deemphasis situation, as well as DC offsets. But my overall question throughout all three of these, especially the first two panels, is when you have these tests set up for your A to D converters, but then yet you see in the second presentation that it's not just about the A to D converters, now we're talking about the actual lines of transfer, if it's AES or if we're looking at USB or FireWire, what have you. It seems like there's questionable variables all along the signal chain here that have to be considered. So how is signal chain actually tested in your A to D converter test? It's not. And then when you get into, it's like, and then where does MADI fit in all this? And especially now with the Ethernet, Dante, they're practically putting out a new driver or something every other week in order to keep the updates on it. And I know this because I'm working heavily with MyTech, working with their Dante card to work in my studios, which I just wired up to handle everything, 192 throughout the whole studio. And it's problematic there because they all based it on 44.1 and 48 because they figured, well, that's all we need right now for live. There's a lot of variables in where we have not addressed how to handle minimizing errors.
Yeah, I agree. I think one of the advantages of my method is that I go SPDIF to a digital recorder, then I take the SD memory card and copy the file to my computer. So I've eliminated USB and FireWire, which, as we saw from the previous presentation, are more prone to errors than AES, EBU, or SPDIF. And I think that eliminates some potential for problems, but you're right, the interfaces along the way, and also what my method does is it completely bypasses the computer sound card, which I think is a very good thing. But you're right, we have to, all of these things, there's a potential for problems in any interface. But by not using USB or FireWire or the more problematic ones, I think it certainly has to help.
Question for you. Thank you for this, by the way. For the Sony 601, on any of the outputs, is there an automatic deemphasis applied?
Automatic deemphasis?
Just
well,
applied automatically, or the
Tascam recorder does it automatically. In the SPDIF data stream, this is part of the Red Book specification. If a CD, or if a digital recording has preemphasis, there's a digital flag that's put into the data stream, and the receiving device senses the digital flag and then kicks in the appropriate deemphasis curve. So it happens automatically, but the flag has to be there.
Right.
Which is often not there for CDs, by the way, because when they have been remastered or something, you find CDs where you have mixed tracks using emphasis and de-emphasis, and they lost the emphasis track in the CD mastering process.
Yeah.
That's just an additional information to it.
You're right, that has sometimes happened in reissuing an old CD. And another thing that's happened, if you're reissuing something that you put out in 1987 and the first incarnation of it had preemphasis on it, you really ought to do the deemphasis and put it out now without any preemphasis. Music and arts programs many years ago issued a live Bruno Walter performance of Mahler's Das Lied von der Erde. The first incarnation, which came out in the late 1980s, had preemphasis. They reissued it about 20 years later, and the replacement disc also had preemphasis. Now, it had the flag on it and everything, but all they did was copy the old disc. They didn't bother to remaster it, take the deemphasis out, and take the flag away. I mean, if you're gonna issue something this day and age, there's no need to have preemphasis on it. And if it's on an old transfer, you ought to get rid of it and remaster it. That's my opinion, anyway. Yes.
I find it curious that as much time and effort as we expend being concerned about fixity in our files, that we have a digital file, we want to be sure that that digital file does not change ever, in perpetuity, that we would take a born digital format, the PCM-F1, and so deliberately change it. So wouldn't we want our preservation master to be a bit copy of what's on the tape?
Someone raised this issue when I gave this presentation in New York, that don't we want to preserve the original bits before we go doing a sample rate conversion? It's a valid point. I would say that I'm not the only one that feels that maybe you don't need to do this. For example, when Telarc took the old SoundStream digital tapes, which were at 50 kilohertz, and they remastered them for SACD going through a DCS converter, they didn't bother to preserve the original 50 kilohertz 16-bit data stream. They went into the DCS converter, converted it to DSD, and that was their preservation copy.
But their intent is different.
But their
intent wasn't preservation. Their intent was
I think their intent I think they had two intents. Yes, their intent was partially preservation, because there's only one working SoundStream recorder now that will play those tapes anywhere in the world. So their intent was to have a preservation copy that would allow them to go back to something that they could actually play, in addition to issuing it in a new format. It's a valid point if you really feel strongly about it. Then I guess go into your computer without a proper digital lock and capture the original bits. But I personally don't see the need for doing that.
It's possible to achieve a proper digital lock and capture the bit stream. As you mentioned, the problem is jitter, because the source of the clock and the playback is the video clock running at 60 hertz instead of at 44K. So all you need to do is to reduce the jitter on the SPDIF stream, which is no more complicated than putting a DAT machine as to rebuffer the bit stream. So you come SPDIFing your DAT machine and AES out, and you'll get a pretty consistent lock. There are also a bunch of things in here that are important to remember, that although this information is correct insofar as the PCM-F1 hardware, it is not true for the subsequent generations. For instance, the issue you pointed out of the shared A to D converter exists only in the F1, and as of the 701 and the subsequent generations, there are two independent A to D converters, so that difference goes away. Also, starting with the 701, the internal clock on the A to D converter is running at 44.1, and the video deck, which can be any NTSC or PAL video recorder, locks to the incoming stream
on the 701
and the 601 and the 501. So these are issues particular to the F1.
Right.
So within the same format, but with the different provenance of the A to D converter, the converter box, it changes after the F1, so that you're recording 44.1 on the tape. What frequently
if you record with those processors, right? Okay.
Yes.
Yeah.
So, and then what happens in playback is that typically the beta deck will use its internal video sync to playback at 2997. So it's recording a black and white signal at 30 frames, but playing back at 2997. So if you can externally clock to a 30 FPS black burst your video deck, it'll play back at 44.1 and not 44.056, Or if you take the bit stream is coming in at 44056, but the file doesn't know that. You just the header on the file gets flagged as 441, and then it will play back correctly. And the preemphasis flag is part of the F1 specification, the 1610, 1630 specification, the SPDIF, and the AES3 stream. So there's a flag in there.
Yes.
And
which I said.
Yeah, well, it's part of all of these standards.
Yes, absolutely.
And the machines are required to have that, so that if you have a CD that has the emphasis flag that has been properly set, then the machine should play it back. Where this becomes a problem in preservation is that if you do as I'm proposing, that you take the bit stream out and you put it into the file, there's no place in a WAV file to carry that flag.
That's right.
So that information is lost.
That's right.
But then, following the recommendations of Sound Directions, for instance, you would have your preservation master file that's a bit accurate example from the original tape, and then produce a production master where you would de-emphasize it in software as you propose.
Yeah. What tipped me off, and I'm maybe getting slightly off subject, but what tipped me off that the Tascam recorder was actually doing the de-emphasis.
Because it recognized the flag.
I recorded the test tones with my F1 processor, and when I played them back with the PCM-601, I could see that 10K was at minus 2.4 relative to minus 10, but the meters on the Tascam were at minus 10. I said, somewhere the de-emphasis is being done, and a bit of investigation showed me that it was, in fact, in the sample rate converter chip. The other thing is that I should mention is that the Tascam has a digital lock light, and if you turn off the sample rate converter inside the DA3000, the DA3000 knows that it's an illegal data stream, and the light lights up red. And when you kick the sample rate converter in, the light.
But that's a design criteria. It's just that the jitter window isn't wide enough.
Well, exactly.
On that particular device.
The way most digital
our ways of doing preservation shouldn't be bound by a specific piece of hardware.
Yeah. Personally, I think the good sample rate converters these days are accurate enough that I don't see a need to preserve the original bits from an F1 tape. If you disagree, well, then by all means do it, but I can't get too excited about it. Let me just say one other thing about the way digital input receivers work, and have worked for quite a long time. A digital input receiver normally throws at first a very wide window on the incoming data stream. And once it determines that the incoming data stream is legal, in other words, it is at a legal sampling rate, 44.1 or 48 or a multiple thereof, it then closes that window and makes it very narrow. And it must do that in order to do jitter suppression. If it leaves that window wide, you will not get optimum jitter suppression. That's the way input receivers work.
But this is not an issue so long as you can acquire the bits, because we're just looking at moving the bits as though we were copying a floppy to a hard drive. However, it is a significant issue for D-to-A performance. Mm-hmm. So you want to suppress the digital, but the jitter performance in an SPDIF stream is bad to begin with,
right,
and terrible off an F1, and so there's another case where we're better off using older hardware because that has a wider window, and some devices will give you the option for have a wide or a narrow window for that jitter.
Yeah, I mean, the jitter is terrible for mechanical reasons on any videotape format, and it's terrible for DAT for basically the same reason.
Okay, I think we have at least one more question.